450? Okay. Thanks. Okay, thanks everyone for coming. It's my pleasure to introduce our speaker today, Professor Edo Berger. He got his bachelor's at Princeton and then PhD from MIT. After that, became a research associate at the University of Michigan and then SUNY Stony Brook, where he got an Alfred P. Sloan Fellowship. After that, he joined the faculty at University of Arizona before going back to where he started to join the faculty at Princeton, where he's been since 2008. He's a member of the National Academy of Sciences and a fellow of the American Academy of Arts and Sciences, the APS, and the AAAS. He is a pioneer in the theory of exoplanets, brown dwarfs, and somehow also supernovae. Today he's going to talk about core collapse supernovae in 3D. Adam, take it away.
Thank you very much, Griffin. People can hear me? Yeah. Adequately? Okay. Okay. I'm going to try to convince you that people who are doing supernova theory actually know what they're doing.
It's about time.
Yeah. No, I understand. This is a tough audience, by the way. I've been here before, so I hope you don't maintain that reputation for very more minutes. But I'm going to try to explain to you in broad outline where we are with simulations of supernovae. And it's taken decades to get where we are. And the reason for that is the problem is complicated. If these things exploded in spherical symmetry from spherical stars, then the problem would have been solved decades ago. But it turns out that these things are unstable to convective motions and turbulence. Now, if the turbulence weren't that important for the explosion itself, that wouldn't be too important. But it turns out to be central to the explosion mechanism that's emerging. And it's a combination of neutrino heating, which is a classical problem. You have neutrino transport in this context, just like photon transport, but different, because the microphysics is different. But you also have turbulent pressure support behind the shock wave. Now, why do you need this? The classic problem is going to be described fairly quickly. You start out with a massive star that has evolved for 10 million years, and then at the end of its life, within about a second, this central object created, which is a so-called Chandrasekhar mass, becomes unstable. And that object collapses within a second to half a second to neutron star densities. The material in the center bounces because when you get to nuclear densities, the material is stiff, and you get a spherical piston that drives out a shock wave. Natural hydrodynamics. But in all simulations, for very good reasons, by large margins, that shock waves stall, and you get an accretion shock. Material from the rest of the star is continuing to flow in. It's continuing to fall. And then you ask the question, how are you going to revitalize that shock wave to give you the supernova that we want to explain? And so it's taken many years to get to the point where we think we've bracketed what happens. Now, getting the answer quantitatively is going to be difficult because this is turbulence, which means it's chaotic, it's stochastic. And so the mapping between progenitor mass and final properties, such as energy of explosion and neutron star mass and nucleosynthesis, is going to have a distribution function. That is what nature is going to do. So it's not as much a physics problem as a real astrophysical problem with complications. And we're starting to see nature in all its complexity in the simulations. And that's giving us perhaps a false feeling that we're actually getting close to the answer. But I will say at the outset that most of our models explode without artifice. Whether they explode exactly as nature would explode is another matter. That still is for us to demonstrate. But getting explosions is easy these days. And this is in part due to collaborators that I've listed here, and to the support of hopefully continuing support. I don't know which direction to look, up there or down there. paymasters. 87A, of course, got a lot of people into the subject, but I want to show this time lapse from Pete Chalice. Some of this was made here. And the point here, I'll do it once more, is that this object is not spherically distributed. So we see from the beginning and many other indications, I just like a movie, that the debris is not spherical. From the very beginning, the explosions are aspherical. And this is another look at 87A, again from Pete, and gives you some idea. This ring has nothing to do with the explosion, but it does have to do with the progenitor, and that's a whole other lecture, most of which won't make any sense, because we really don't understand this in detail. But this, also, is a distribution of heavy elements in Cas A from X-ray data. And you see this green is where the iron is, the red is where the sulfur is, and there are other distributions as well. But again, these are not spherically distributed. In fact, the iron is distributed in big clumps. And this has to be mostly, not completely, but mostly a result of the instabilities in this explosion itself. And then there are subsequent instabilities as the blast wave moves out through the debris. That's the subject of another talk as well. But we see that. And there's a jet-counterjet structure which seems to be subdominant energetically, but which is very fascinating. We also have from a new star the the titanium-44 radioactive distribution. And you see that there's a distribution of iron and a distribution of titanium-44, where they're not coextensive. Where you see one, you don't see the other, and that is anomalous. That is something to explain. But the point is, it's not spherically distributed. We also have data on the explosion energies gotten from light curves, and this light curve simulations are not perfect, but this is the state of the art from Morozova et al. And inferred ejecta masses, which are close if you form a neutron star to the ZAMS mass, or at least the mass when it explodes. This will be within 30% of the ZAMS mass at solar metallicity. And you get energies of explosions that are generally between 10 to the 50, 10 to the 51 plus ergs. It's not just 10 to the 51 ergs. And for lower mass progenitors, we get lower energies on average. The higher mass progenitors generally always have higher energies. And that's a target for theory. Now, the basic backdrop is, as I mentioned, you have a progenitor star that has the so-called onion skin structure. I'm assuming that most people understand the basic astronomy, so I'm not going to go into any of the details. You have an iron core, which again becomes unstable by the Chandrasekhar instability. And then over hundreds of milliseconds to seconds, you get the collapse bounce to shock formation, a protoneutron star formation, a neutrino star is produced, and that shock needs to be revitalized. In many of our models, the revitalization happens almost immediately now. The turbulence helps a lot. In most models, it still takes about a few hundred milliseconds. That's a long time in our game. That's actually 100,000 time steps in a simulation, where a time step is a microsecond. I'm not going to, every time step costs, well, you don't want to know. I don't want to make it public. But this is the thing that we want to explode. There's accretion, there's a standing shock wave, there are a lot of neutrinos coming out, and this is convectively unstable. This is the type of distributions we're getting in our models. This is, you're supposed to be on something by watching this. This is near the shock wave, just after the bounce and just as the explosion is starting. These are matter pellets, tracers coming in, more or less spherically in a spherical model without rotation. And then there's turbulence in here. And these are isoentropy surfaces colored by electron fraction. Electron fraction is a composition variable, and the electron fraction will determine what the nucleosynthesis in the inner region is. It'll determine the isotope ratios for iron. It'll determine it'll determine a lot of it. People may have noticed in the kilonova context that people were really wondering about the production of the lanthanides and the production of the R process. That production is directly connected to what that electron fraction is. And in that context, they needed to be below 0.25, which is very neutron rich. That's the electron to neutron plus proton ratio. Oxygen and carbon are 0.5, hydrogen is 1. Hydrogen-helium mixtures are 0.83, things like that. This is mostly 0.5 out here, but I'm going to show you what we get. Okay. Now, it's not going to be all eye candy, so you have to read something, and there are words here. So just in case you people in the back can't read, I'll just mention the basics. The stalling of the shock is a generic thing. It happens because that accretion produces a ram pressure that's hard to overcome initially, because the mass accretion rates start out at around 10 solar masses a second. That's right, 10 solar masses a second, not a year. Okay. And it's also the case that the neutrinos that are produced in the beginning from the shock wave as it moves down the density gradient liberate a lot of energy, and that saps the shock. In fact, that's the dominant effect. There's the photodissociation of the nuclei that are coming in that softens the material, and then there's the neutrino losses. Again, there's a lot of physics here I'm going to go through fairly quickly. The neutrino emission, though, continues, and it continues for many, many seconds. The neutrino energy deposition behind the shock on those neutrons and protons behind the shock is really the agency, and that's the ultimate source of energy for the explosion, by and large. But there's also the turbulent pressure. And that when you put energy into turbulence, you have a more efficient stress. The effective gamma of turbulence is actually 2, as opposed to 4/3 for electron gas, or 5/3 for normal stuff, or 1.25 or something for the air in this room, depending on the temperature. And so you get a much more efficient conversion into pressure if you put that energy into turbulence. You get a delayed explosion most of the time. It's very hard to avoid that failure. The supernova explosion is a critical phenomenon in the sense that once the control parameters are right, and that's determined by nature, then it bifurcates, the solution bifurcates from an accretion solution to asymptotically a wind solution. So from ordinary differential equations that bracket the supernova, you go to partials in the middle that is the supernova. Okay? And multi-D is necessary. So turbulence crucial. So the history, and I've mentioned this to people already, and this is an important point. Many years ago, 1D was the state of the art, and we could do many 1D simulations and maybe 2D simulations in a year, And then we evolved to the point that the codes were faster and the computers were faster, that then we could go to many 2D simulations in a year. And maybe 1 3D simulation. Now we're at the point where, in fact, we can do many 3D simulations in a year. And fortunately, we don't have to go any further. So that's important is so we can make lots of mistakes. We have to be able to not do one simulation that takes a year and then find out we did it wrong, or it's just one set of parameters. We have to do a lot of parameters. That's not just because nature has a lot of parameters. It's that we have to gain our intuition. You have to gain your intuition with something that is close to reality. We're trying to get it close to reality. And in 3D, we have the chance of getting it close to reality. So we can do multiple 3D simulations per year, and that's what's happened. And what I'm going to show you is a result of a program where we've done 33 3D simulations over 2 years. And that's a game changer. And that's because of the code, and that's because of the new iron, the big iron that's being made available by the Department of Energy and the NSF in particular. And unfortunately, we do need big supercomputers. And those simulations still take a few months to do, and a few tens of millions of hours each. Now, there are interesting physics issues having to do with the neutrino-matter interaction. It's MEV physics, and nuclear physicists think they know MEV physics, how the neutrino interacts with MEV energies with normal matter. It's mostly true, but when you get up to high densities, you have nuclear interactions, and your neutrinos are scattering or absorbing off of nucleons that are correlated one with the other. And it's just like having a synchrotron light source looking at doing X-ray crystallography. What you see is all those Brouillard patterns. That's because of the correlations of the positions in the lattice. Well, if you have something similar where you have interactions between the nuclei, then it really makes a difference what the neutrino-matter interaction is. Now, that's at high densities. And for 20 years, we've been trying to narrow that down. Okay. There's also the accretion of the silicon-oxygen interface. When you do these stellar evolution calculations, you get a density profile that has iron in the inside by and large. Then you have silicon and oxygen, et cetera, and you go out in the onion skin structure. Those interfaces generally are entropy jumps. And when you have an entropy jump, and when the pressure is continuous, you have a density jump. And that means the density goes down when the entropy goes up. If you accrete that density shelf, then all of a sudden you have no accretion RAM. But you still have the neutrino luminosity, and that can kick it into explosion. Half our models explode when you accrete the silicon-oxygen interface. The code we're using, and this was presaged at lunch today, is called Fornax, if anyone was at lunch. And it does 1D, 2D, 3D multi-group radiation hydrodynamics. It's not perfect, but it's the best code out there. It doesn't do full GR, but it does approximate GR. We have the redshifts in there. We have the strengthening of gravity. We need to do it with GR, but that's a much more complicated effort because the complications come with the transport. You want to do multi-angle, multi-energy, multi-position, multi-species, multi-time calculations. The multi-angle is what's slowing us down. We're doing everything else. So we have a spectrum of neutrinos that aren't in equilibrium. The transport puts them in equilibrium if that's the appropriate thing. We have multiple neutrino species. We have vector fluxes, so the radiation can go in all sorts of directions, but it's moments, angular moments. And what you need is to be able to solve for the distribution function. You need to be able to solve for the specific intensity. That's many angles. That's another set of dimensions. And that would be something we're going to do in the future, and we have a pathway to that, but it's still going to be expensive, and that requires new techniques. Okay, again, it has all sorts of bells and whistles. The number of these things is just to indicate you're not supposed to read this and just be impressed. And so we have a number of papers that have been published using the code, et cetera, more in the pipeline. It has lots of bells and whistles. One of the interesting things is you have to be able to do Compton scattering of the neutrinos off of electrons. It's not Compton, but it's the similar thing, because you need to have the redistribution of the neutrino energy due to inelastic scattering, because the difference goes into the matter, which heats the matter that helps drive the explosion. It turns out to be a 10 or 15% effect, but we're starting to be interested in those things. And so we have inelastic scattering in there. We have these in-medium medi-body response corrections. We have general relativistic gravity in there with gravitational redshifts. We have the velocity redshifts as well, which you need to include in the transport. So there's a lot of terms in here, but it's not perfect. We also use polar coordinates because they're the natural coordinate system for a star. I wanted more laughs out of that one. Okay, let me start with the basics of we start out with somebody else's progenitor models, massive stars that have been evolved to the point of collapse. We inherit those. It turns out that those structures, the density profile in particular, is crucial to the outcome. And those models have not converged. And so here's an example of density profiles for one group, one group from 9 solar masses, 10, 11, 12. Again, from 8 to who knows what the upper limits are. Masses is what we're talking about for core collapse, supernovae. Whether they form neutron stars or black holes is still an open question. Most are going to form neutron stars, certainly down here. But the black hole formation is still an open question. But you see these density profiles. Here's the Chandrasekhar core. There's slight differences from one to the other, entropy differences and this sort of thing. The outer regions here, though, have very different density profiles. A shallow density profile, there's the silicon-oxygen interface, by the way, and very steep profiles. It turns out that these steep ones explode really easily, and the shallow ones explode really easily, and the middle ones are a little problematic right now. Now, whether they're problematic because of our numerics or their nature is saying they're less explodable or don't explode is an open question. But they're not a large fraction of the mass function. But these types of profiles keep in mind. Because when you look at different groups over different years, the same object has very different profiles. This has to do with the physics they're using for the convection, for so-called semi-convection, for the C12 alpha gamma nuclear rates, a number of things. And that translates into variation. Right now, there are a few groups around the world that are now doing these calculations after core oxygen burning in 3 dimensions. Stellar evolution in 3 dimensions for the entire evolution of a star is not possible. There are just too many turnovers during the evolution of the star. But the last phases, you can do it all in 3D, which is amazing. And so that we're going to get better progenitors that have real clumpy structures that are going to collapse. And I have a funny feeling that's going to make it rather obvious to everybody that we know what we're doing, because the explosions, I have a funny feeling. I don't know what type of funniness that was. Because those progenitor structures, not just the average density profiles, but whether we have matter motion going out when the thing is collapsing in, makes a big difference in the accretion rate as a function of angle and how it explodes. Because all these things explode aspherically. They always find a direction and go there. Okay. And this is just to emphasize the point. This is the same group. Don't look at the details because I didn't make it so that I actually made it one-to-one comparison. But just pretend it's a one-to-one comparison for the same group, but different years. And these models, if you look at an individual object, are all different. These things change. So we have not converged. And the problem is, when we do simulations, here are two models. See those density profiles? 10 to the 10 grams per cubic centimeter. It's the same thing I showed you before. And here's the outer envelope. So 1.5 solar masses right there, interiors, like a radius. That's the center. Here are two models right there. One is 15.01 solar masses. The other is 14.99 solar masses. And the blue one is 15 solar masses. So the ones bracketing the blue are this dash curve and the green curve to within 1/100th of a solar mass. This is what we have to contend with. Now, whether this is true is not obvious. But there is some sort of chaos in the modeling these days. It's not just theoretical. The reason this is interesting is that this model, these two models, let me see the two models, yes. This model, the blue model, does not explode. The dashed model does not explode, but the green one does. And they're within 1/100th of a solar mass. Now, it does not explode in our implementation of the codes without rotation. So there may be at our resolutions. There's also a binding energy penalty. The energy exterior to, for example, our computational grid, the outer star, is bound. And so we have to overcome that binding just to get to zero energy at infinity. That energy for most of the low mass progenitors, 15 and below, is not that large, although it can be about 0.3 times 10 to the 51 ergs. But when you get up to the higher masses, it could be 1 times 10 to the 51 ergs. And some of these have significant binding energies, and that may be what makes a black hole. We can't explode it. You start out exploding it, because a lot of these things start out exploding, but then there's all this binding energy to overcome, and the stuff falls back. You form a black hole. You might get a supernova. You might get a weak supernova at the same time as you have a black hole. So that's been the story for a long time. We just can't simulate that long most of the time. But eventually we'll be able to. I want to just show the difference between 2D and 3D. Here's a 2D simulation. Here's a 3D simulation. Exactly the same model. Okay, this is just a slice. 2D, because it's axisymmetric, oscillates up and down like that. That oscillation made people think all sorts of things about this sloshing up and down motion. Turns out to be an artifact, mostly. Driven by turbulence, that's true, but in this context. Both these models exploded, but this one just found a direction. Wasn't along the axis, fortunately, of the code, of the calculation. But it doesn't do the same sorts of things. Intuition had to be reformed by going to 3D. Okay? You had to go to 3D to actually get your intuition. And this is just an example. Slices, same model, but this shows that artifact. 3D looks much better. And this really, well, no, I'm not going to show it. This really makes the point. This is a Sean Couch show. This is a dowel, but this is the distribution you actually have when you're doing a 2D simulation. It's axisymmetric, so it goes around like that. But that's what we get normally. Okay, so we've used this code Fornax, and I want to call attention to particularly Dave Vartanian, David Radice, Aaron Skinner, Victoria Morozova, Josh Dolans, were key to various aspects of these simulations. And developing parts of the code, but certainly the science. And this isn't a summary of everything we've done. This is just an example. This is the average shock radius, 100 kilometers, 200 kilometers. Things sort of stall at around 100 kilometers. That's the stall of the shock. Things go up. Some models don't explode. Most of them do. after a delay. Some explode pretty soon. Most of those that explode pretty soon are low mass, 11 solar masses, 10 solar masses. Those are pretty easy. We see explosions in 2D and in 3D. You don't see them in 1D. You need the turbulence. There's other aspects to it as well. The matter dwells longer near the shock, and it's near the shock that the matter can absorb the neutrinos. So the time scale that a Lagrangian mass element spends in this region that can absorb the neutrinos is longer in multi-D. In 1D, it just goes straight through. It doesn't have a choice. So those two things make multi-D rather important. Okay, so here's an example of a 16 solar mass model. This is entropy. There's the protoneutron star that's just formed. It's an isodensity surface. The shock wave is over there. Colors change as the entropy changes. If you get up to red values, that's higher entropy. This thing is exploding. But see how it explodes. It explodes in big bubbles. There's a dipolar structure. It is actually continuing to accrete along the some sort of equator, which it discovered. It was random because it's not a rotating model. So you still have accretion and explosion simultaneously, which you can also not do in 1D. In 1D, when you explode, the accretion sort of stops, right? If the accretion stops, you don't have the accretion luminosity. You just have the diffusive luminosity from the core. You need both. That both help. When you have multi-D, you can break that symmetry and you can have simultaneous accretion powering the neutrinos that then come out in all directions and power the explosion. Another important aspect of multi-D. You get simultaneous accretion and explosion. Okay. This is the same model, but the colors are now the electron fraction, the composition. I'll figure out which one is which. So there's below 0.5, so it's neutron rich, above 0.5, so it's proton rich, and at 0.5. And 0.5 is a lot of this red stuff. The blue stuff is above 0.5, and the purple stuff is below 0.5. The point is that the nucleosynthesis associated with these models is directly connected to what that value is, and it's not coming out spherically. You'll also notice there was induced rotation there. The net angular momentum is 0, but you can get rotation induced in these objects when the outside goes one direction, the inside goes the other direction. You can actually induce rotation in a neutron star that didn't have any rotation to begin with. Some people have suggested that that's the origin of neutron star spins. I don't think that's true. I think the stars naturally spin, but it's the component. We can't get more than about 500 millisecond periods, but that's pretty fast. So that's an interesting component. And this is the structure that looks like. It looks like a wasp waist, right? There's a thorax and all the rest. We can make all sorts of biological analogies, you'll notice, looking at these things. Some of them rather gruesome. But that's what we were getting, so truth in advertising. Okay, and that's that asymmetrical distribution of heavy elements. This is not spherically distributed. And to make a point, this is the same sort of thing. There's the neutron star that was burst, that thing right in the center. It's just an isodensity surface, but it's staying behind. We did it naturally. We didn't put it there. Which way is what going? The kicks are going to be another talk. That's an important question. So this is just a collection of 9, 10, 11, and 12 solar mass models. They do similar things, different things. These are zoomed outs, right? So we're zooming out, and there's the shock wave. But they all have similar structures, high order L modes, as well as dipolar modes, etc. You can do a YLM decomposition of the distribution of stuff, or the shock wave, and you can make some traction. There's the neutron star in the center right there. But do you see the types of structures that we produce? There's that wasp waist. That really makes a big difference. We get a lot of neutrino luminosity at the same time that if it were a spherical explosion, it would be turned off. However, not all the models explode. These are exploding models up here, but I have exaggerated one that you'll see what happens. Now, green is low entropy and red is high entropy, and you see the evolution to high entropy. The higher entropy is what really drives it. That's due to neutrino heating. And you want high entropy. I'm not going to explain. Entropy is not something you deal with on a daily basis. But this one didn't explode. This was the 13 solar mass model. That's right in the middle of the mass function. That should be exploding. In our calculations, it did not. And one of the reasons was that silicon-oxygen interface was much more muted. There were a couple of other things, but it was a subtle mapping from the progenitor density structure to the outcome. This is not something you can capture easily with a one-parameter family, not even a two-parameter family. I think I have to do this. In Britain, you can't do this. Nobody goes to Britain. No, Winston Churchill, when he was making the V sign, he did this, and that's up yours. What he meant was this. This was called to his attention, and it was made very clear that he was of the upper crust. Okay, so this is the 13 solar mass model. It has all our bells and whistles in there. There's the neutron star, and it's green, lower entropy, but the neutrinos are heating it, etc. But this does not explode, but watch what it did. Shock shrinks, and then it starts to wobble. An M equals 1 spiral arm spontaneously developed. That will AM modulate the neutrinos. That will AM modulate the gravitational waves. A signature like that would be very interesting in gravitational wave detectors if we're lucky enough. The rates aren't large. But we have a whole paper on this. And so this is just a sample of 25 solar mass exploding model where there's the shock wave, and you can see all the turbulence here, and here are example accreted blobs. You see the color, again, painted by YE, and you notice that it's purple on the bottom and yellow on the top. There's an asymmetry in the ejection of the YE material. It's really interesting. I'm not going to go into that. That's another talk. But we see that fairly generically. And this is what we get. Okay. Too many technical details here, but I will call your attention to, this is just 2D, 3D comparisons in various parameters. I want to look at this. This is the efficiency of neutrino energy deposition. You have a certain luminosity coming out, and then a certain fraction of it is absorbed. It's not 1%, it's 5% to 10%. At this phase, the energy deposition is pretty significant. Just because you have 10 to the 53 ergs coming out of neutrinos and a 10 to the 51 erg explosion doesn't mean you take the ratio to find out what the efficiency of the process is. The process happens in the first 2 seconds. During that time, those ratios are much more propitious. Here are the neutron star masses left behind. These are the baryon masses. And so here's about 1.15 solar masses baryonic. And then this one grows to about 1.35. Then we get up to 2, a little bit higher than 2 baryonic. These things, the binding energies eventually are going to be fairly large, and so you have to subtract the binding energy, which is about 2/10 of a solar mass, 3/10, 1/10 of a solar mass, and so you have to make that correction. And we get neutron stars left behind, gravitational masses that vary between about 1.2 solar masses and 2 solar masses. Now, the mapping between the progenitors and these final states is not something I would want to quote. That's still in flux, but that's one of the things we want to predict. But what we can do is predict all the masses of neutron stars. Now, whether we're predicting them right is wrong. We don't know. Now, this is the radius of the protoneutron star in there. That's the 10 to the 11 solar mass surface. And you see, even after about a second, it's still about 30 kilometers in radius. There's still a lot of action to go. It's also the case, and that's another subject for another talk, in here, it's convectively unstable. You actually have a real star. In the inside, it's radiative, then you have a convective zone, then a radiative zone, then a convective zone. You can't handle that in 1D. That inner region that's convective actually transports energy up to near the neutrino sphere and boosts some of the neutrino luminosities. This is just like a star. But we're actually simulating the effect of convection on the radiation because it's all in there. I just think that's cute. Spatial resolution. There are a lot of dependencies here. So we did a whole spatial resolution study, and Hiroki Nagakura led that effort. This is the inner 60 kilometers, and this is the resolution. So this is our low resolution. This is a medium resolution. This is high resolution. It's just 60 kilometers. We go out to 20,000 kilometers. The high resolution, we use a dendritic grid. It's like AMR, adaptive mesh refinement, but we don't adapt. We know ahead of time what the resolution needs to be, and we just leave it like that. The adaptation was going to be gilding the lily. We can do that. We don't really need to because we know what we're focused on one particular problem. The low resolution one, exactly the same model, 19 solar mass model, did not explode. Fortunately, as we went up in resolution, they started to explode. If it went the other way, we'd be in trouble because nature has infinite resolution. Okay? And as you go up in resolution, it gets more explodable. A lot of people's 3D models in the literature probably just didn't have the resolution necessary to show explosions. I don't know which ones, because it's their codes, not mine. But in our code, we see this. And this is the resolution that most people use. This is 64 angular zones in the theta direction, all the way around. And it's 128 in the phi direction. And then we have the same radial direction. This is just angular directions. We have 678 in the radial direction, which is also more than most people use. And this one was 4 times that. 2 times 2 in those directions. And these are just the differences in the resolution at different times, low, medium, and high resolutions, just to show visually what those differences were. And here's the turbulence. This is the Reynolds stress divided by the total pressure. Reynolds stress is important in figuring out what the contribution to the stress is due to turbulence or convection. And the high resolution one had higher value. And here's the shock wave right over here. And by and large, going to the higher resolution really made a difference. The green curve is medium resolution, and most of the time, certainly at later times, the green and the red were the higher ones, and the blue was the lower one, and that was the one that didn't explode. And we can do Mach numbers. We can go all sorts of details. We have the Kolmogorov-like spectrum. We're not resolving the full inertial range, but we are resolving the large scales. It's the small scales we're not resolving. That's something for the future. That requires really high resolution. And nobody can do this at this stage. But as you increase the resolution, we have more components, more L components in the turbulent stress. And the rest have actually saturated. Okay, and this is just showing the explosions. I do have time. Okay, so this is the low resolution. And I think that's the low resolution, and that doesn't explode. But you see it starts to wobble. That's that same m=1 mode. Failed models at late times that don't rotate generate these spiral arms. But that's just rotating around the object, which is very interesting. If you have rapid rotation, it does the same thing. But there's not as much angular momentum. Now, I mentioned YE, and the nucleosynthesis is a function of that, what the ejecta composition is. And so this is just a collection of our the amount of mass at various YEs. And you notice here's 0.5, and most of this stuff is above 0.5. We have a little bit neutron rich. Most of it is proton rich. You can't get an R process out of this. You can get the RP process. You can get a number of things. You can get a lot of nickel produced. This is a log plot, so there's not a lot of mass coming out. It's mostly over here in this peak. But this is something interesting. And the reason for it is that these are electron-rich objects. You start out with a white dwarf that has a net electron number, not an positron number. And so you trap lepton fraction in these objects, net electron-lepton number. And that converts into electron neutrinos, more so than anti-electron neutrinos in an integral sense. They're sort of similar in the beginning, but the net effect of the lepton loss is net lepton loss. The electron neutrinos and the anti-electron neutrinos are absorbed on the matter. The electron neutrino absorption on neutrons is a big heating source. Produces protons and electron. The anti-electron neutrino absorption on the protons produces neutrons and a positron. That was the experiment that was done by Reines and Cowan outside the Savannah River reactor to detect neutrinos for the first time. They used exactly that reaction. We know that cross-section. Okay, that was in the 1950s. But you have a net lepton number coming out. That means that electron neutrino absorption predominates, and it produces electrons, not positrons. So you take the difference of those two effects, it's net electron deposition. So if you stay near the oven while you're being ejected, you have more of a chance of absorbing, increasing your electron fraction than decreasing, because there's a net positive electron lepton number in the object that is driving things. If you eject it really fast, you start out at low neutron rich, then ejecting it fast doesn't allow you to get up to the high values. So you can eject neutron-rich material, but it has to be ejected really fast. And in these models, in almost nobody's models, do you eject fast. But you have to eject fast in kilonovae. Because in kilonovae, you have exactly the same sort of thing. You have emerging neutron star, you have a lot of neutrinos. The neutrinos are going to absorb, produce electron fraction. You start out with a neutron star, so it's really low YE, neutron-rich. And then you start driving up the electron fraction. If it ejects fast, you get the R process. If it ejects slowly, you don't. Same as supernovae, except that's what happens. At least that's what we think happens. Now, you have to do this in 3D, because what you're doing is you're looking at various trajectories. You saw that dowel. Exactly how that matter emerges and how long it's irradiated depends on the details. And 2D and 3D have different trajectories, different behaviors. And so here's the 2D simulation. You see we have a lot of neutron-rich stuff. In the 3D simulation, we have very little neutron-rich stuff. Now, whether this is generic remains to be seen, but it's something of interest. Okay. Of course, as I've been mentioning, neutrinos are crucial to this, and the neutrinos have been detected from 87A. We got 19 events, 11 in Kamiokande, and 8 in the IMB detector. The other detections aren't credible, despite what they would say. However, if there's a galactic supernova, given the detectors that exist now, such as Super K, detectors that are planned, such as Juno and Dune, they are going to be very massive. One in our galaxy is going to be closer than 87A, and you're going to get thousands of events. Thousands of events means you're going to get a light curve, and better than a lot of X-ray light curves. Although, I shouldn't say that. Every time I come to Cambridge, I got to be careful what I say about X-rays. I love X-ray astronomy. I almost went into X-ray astronomy. Anyway, that's a different issue. So the neutrino detection is going to be a diagnostic of the internal dynamics. You're going to watch in real time what's happening. You're going to watch the stalling of the shock. You're going to watch the development. You're going to probably see the explosion. You're going to see the cooling of the protoneutron star. So here's examples of the detectors. Super Kamiokande with much less of its water. Ice Cube, Dune, and Juno, as I mentioned. These are in process. These exist. This may be followed by Hyper K, and there are smaller detectors that are still large for galactic supernova. They get hundreds of events. That's going to be amazing. And then cross sections. We know the cross sections pretty well for the interaction with the detector material. Some of these cross sections, compared to photon cross sections, most photon cross sections, these are pretty small, but you need a lot of mass, and with a lot of mass times a small cross section, you can get some real science. Okay. Here's that breakout burst. Here's versus time. Here's the shock is formed, and when that shock goes down the density gradient, it liberates all sorts of neutrinos, and they give you a big breakout burst of electron neutrinos. Then you get mu neutrinos, tau neutrinos, anti-electron neutrinos, and these signatures are all predictable and predicted. Now, you can do it for lots of models. This is after the breakout burst. This is the electron neutrinos, the anti-electron neutrinos, the mu's. My only point here, the thin curves are 2D models. The thick curves are 3D models. Not that much different. My point here is that there's a systematic dependence on progenitor structure of the values here. The time at which these things change is directly connected to the position at silicon-oxygen interface. Accretion changes, the luminosities change, the signal changes. Whether it explodes or not is directly connected to the neutrinos. If it doesn't explode, it's going to be a higher event rate. And when it forms a black hole, it's going to turn off immediately. It's going to go off within a millisecond. That's a signature, a predicted signature. And average energies of the neutrinos, they're on the order of 15 to 20 MeV. These are RMS energies. And the different species have slightly different values, but not that different. There's been new numbers that have been developed. Non-exploding model signal rates, exploding model signal rates. But look at the event rates. That's 6,000 hertz. Okay? These numbers are real. It's just the detections that are anticipated. Okay. We can do this for... there is neutrino oscillation, though. And that's one thing we haven't included in the models. That's a big unknown. And that you should carry away. We don't know what that's going to do. And there are different types of neutrino oscillation. The MSW effect isn't going to happen because the densities are too high. But there are other oscillation effects, neutrinos going over other neutrino fields. There's lepton numbers. In the sun, you get neutrino oscillations because there's an electron distribution that has a lepton number. And you have the electron neutrinos going through it, and that gives you refraction effects. And you can get resonances. And we've seen that in detectors in detail. Nobel Prizes have been awarded. You usually think that those are for good reasons. In our context, we have electron neutrinos coming out. We have electrons. We have different types of leptons, et cetera. But the neutrinos themselves provide a background you don't have in the sun. So that causes nonlinear problems. Now, the anisotropy of the neutrino emissions, this is exaggerated here. This is the integral solid angle integrated neutrino luminosity in units of 10 to the 52 ergs a second. That's a lot. And this is the angular distribution of that particular model, where the color and the bulge are redundant. The luminosity is 5% higher in the red and 5% lower with the blue. And you can see, and then it bulges out in the red when the luminosity is larger, and it shrivels in. It goes in the blue when it's blue. And you can see there's an anisotropy in the neutrino emissions. We're going to get only one direction. So people be aware of this type of variation. And in fact, if you look at different models, this is the RMS variation in the neutrino emissions in angle. And you get 10% effects, by and large. Now, this is a detail, perhaps, but we can now calculate this. Okay? Gravitational radiation, of course, has been in the news recently. Supernovae are good sources of gravitational waves. Not as good as merging neutron stars or black holes. Those will give you solar masses or quarter solar masses of mass energy equivalent. But we can get 10 to the minus 8 solar masses. Now, that doesn't give us the universe as our playpen, but it gives us the galaxy and maybe the local group. So what does it look like? Again, there's lots of detail. Don't worry about the detail. This is another talk. There are many wonderful people who have been involved in this subject. This is a simulation, though, I want to show. So this is a 2D simulation, and here's what the hydro is doing. Here's 200 kilometers, et cetera. It's bouncing around, and here's the corresponding gravitational wave signature. It looks very stochastic, bouncing around. It doesn't look predictable. But notice what happens. When it explodes in one direction, which is also related to the direction of the kick, you get this type of climb in H. This is like a DC component, but it's a low frequency. It's about 10 hertz to a tenth of a hertz. LIGO can't see this, but there are space-based detectors that are being suggested that could see this. And this is directly connected with a anisotropic hydrodynamic phenomenon in the core, in the belly of the beast, that could be seen directly in gravitational waves. Now, these are various gravitational wave signatures. It looks very messy. This is the bounce phase, and this is bouncing around. This actually stopped emitting because there was, what's happening here is that you have a core where material is still accreting. If it accreted spherically, it wouldn't be much, but it's accreting aspherically. And so you have plumes hitting the surface, and what it's doing is it's causing the core to resonate, causing it to oscillate. What you're seeing is astroseismology of neutron stars. Now, people have been trying to find this see the oscillations of neutron stars for a long time. And there's suggestions people see torsional modes and this sort of thing in old neutron stars. But when a neutron star is born, its fundamental modes are being excited. P modes, G modes, F modes. And the dominant mode that's coming out here is actually the F mode of the oscillation of the protoneutron star. People who do astroseismology for regular stars, they'll know about these modes. There are normal modes that are excited. And the one that's excited most is the F mode, because the plumes hitting the surface are just where the F mode has a lot of wave function. And so you see these various signatures that would be predicted, but a lot of noise in here, and these are all with plumes hitting the surface, etc. When we get a spectrum, it's in the hundreds to 1,000 hertz region, and this is comparison with detectors at 10 kiloparsecs. But what I want to call you, and then there are differences between 2D and 3D that are important. But what I want to call your attention to is a spectrogram, which is in frequency versus time. And you see that ridge? You see those ridges? That's the signal in H. That's the signal in the spectrogram. There's a ridge in all models that is the F mode. That's a prior for every model. It's not simply a stochastic mess. And there's almost nothing down here. And this is just another model. This is for details about, there's so-called SASE instability that people have pushed for a while. That's down here. The dominant term is up here. And you see this when the models don't explode mostly. And when they do explode, you rarely see the SASE. It's neutrino-driven convection. If people have seen this term, it's been exaggerated in its importance. And this is just showing a systematics of models. Gravitational wave energy radiated, not a lot, but a lot in some contexts, versus the turbulent energy just above. It's the turbulence that's driving it, and you see a nice, not linear, but on a log-log plot, linear relationship. There's this one point down here that anchors this, but this is nice. So we understand why it's radiating gravitational waves. Okay? We can also do this look at this frequency, this F mode versus time, and normalize it to the dynamical time. Is 1 over the square root of g rho, suitably in frequencies. And for all the models, when you normalize it like that, they're almost the same value as a function of time. This is 9 to 60 solar masses, which, by the way, exploded. This is within 15%. That's the prediction. Here's the F mode frequency. Goes up to 1600 hertz in these models. And you can see, and this is the normalized one, and you can see, fundamental, yeah. And you can see is for different progenitors, you still have the same basic behavior. Same basic behavior, same frequency range. This is the total neutrino energy radiated. Has to be monotonically increasing, right? And you see a range here. And you can normalize that to the total amount of energy available, and you can see there's a small range. You can do the equation of state dependence for that ridge. Different equations of state. The red has now been eliminated by nuclear physics. These two are still there. Different equations of state don't give hugely different numbers. And the frequencies increase with time. You can include rotation. If you include rotation, you get, here's without rotation, here's with rotation. You get this big signal here. It also changes this stuff in here, which we're working through. But this has been in the literature for about 35 years. We're just reproducing this with our code. If you increase the rotation rates, initial rotation rates from nothing, here's something, and here's some rotational signature, another, as it goes faster and faster. Okay. Did you hear that first chirp? I'm going to do it again, just because I like it. You don't have to. That's rotation. Now, I'm going to do, don't worry. I don't like these things, so the thing you should notice is the frequency is always increasing. It's always increasing in a predictable way to within 15%. It's almost independent of the equation of state, but not. Almost independent of the progenitor, but not. But it can be normalized to be pretty close. So we have predictions. The rate with which those frequencies change is directly connected to the rate with which the thing shrinks. The shrinking is directly connected to the neutrino losses. If you have the neutrino data, you can analyze the gravitational wave data that much more precisely. They support one another. Yes, I have an obsession, I know. This is not boosted. This is in real frequency space. Okay? You'll hear Lisa signatures, right? They're not in the audible range. We have the audible. These are other models. This sort of stopped, but they all increase in frequency. Okay, these are the energies that are radiated. If you calculate for just a few hundred milliseconds, it takes a while for convection to start going and for the jostling to start, etc. So you start out low, and then you get up to a value, and a lot of calculations in 3D stopped right here. 10 to the minus 10 solar masses radiated. But if you just keep it going for another second, you get 2 more orders of magnitude. Just be patient and get the resources, because this is really expensive. Excuse me?
You don't have to be very patient.
That's true. Okay. And the detectability of these things is directly connected to the square root of this. So you can go out a factor of 10 in distance, because we can do late time simulations and not just early time simulations. All right. Now, you can compare to the putative sensitivity of the Einstein telescope the Europeans are pushing and the Cosmic Explorer the Americans are pushing as part of the 3G effort to go beyond the LIGO constellation with CAGRA. This would be amazing. But the advanced LIGO, A+ as well, is going to be amazing as well. And we'll be able to see probably out to certainly the whole galaxy for the garden variety core collapse. And we might be able to see out to Virgo if certain things happen. Not Virgo, what am I talking about? M31. I was asked once by someone at the NSF, who will be nameless, if I could I actually make a prediction that you could see gravitational waves from supernovae out to Virgo. He said if I could do it, he'd give me another 50,000 of my grant. You know why I don't mention his name. Oh, did I say he? Okay. So these are other people's models. They've done some nice work on this. I just want to be ecumenical. And they all get high frequencies. They didn't carry out as far, but this is the comparison with the Cosmic Explorer, the Einstein telescope, etc. There's a significant difference here. And they've been focusing on this for merging neutron stars and black holes. These things will see all the black holes in the universe merging. That's an amazing statement. They won't be able to do anything with them because they're going to get so many, and astronomers won't be able to follow up. They'll get tired of it very quickly. But they're going to get an incredible statistical sample here and incredible data. So I'm going to summarize with the following, and just recapitulate what I've said. By and large, turbulence is a key enabler of explosion, so multi-D was essential. But neutrinos are always an important factor. And there are diagnostics in both the gravitational waves and the neutrinos that allow you to watch in real time, in principle, what a nearby supernova would look like. But aside from that, what we seem to have right now is a converging model that, even though it depends on the progenitors, we don't know what the rotation rates are for these progenitors, we still have to improve our numerical game. There is still neutrino matter interactions that we would like to refine. Almost all models explode. Some don't for reasons that we think we understand. So there's no problem at all, and this is without tweaking anything. This is just emerging from the simulations that we can now do. And the real breakthrough has been getting tools like Fornax, but also being able to do many simulations. And as I said earlier in the talk, to make as many mistakes as is natural in the theoretical project as quickly as possible. And we can afford that one 3D simulation or even 2 3D simulations are in the can because we have more. And we can develop the intuition necessary to really understand what we're getting. Progenitor structures are still crucial, but then we're going to have 3D progenitors pretty soon. And in fact, we have a model from Couch that's running right now where he's done a 3D progenitor, and we want to see what that does. And we're comparing it to the MESA version, which is a 1D progenitor. And that comparison is, I think, going to speak volumes. There's a crucial role for the microphysics, but there's a lot of components to this problem. I don't want to leave you with the impression that the problem is solved. The real things have to be connected to data. Can we really explain the neutron star masses, the pulsar kicks, all the nucleosynthesis? In the near term, we're going to be explaining the supernova energies in some detail. Once that's done, if I come back in a few years, I will be a little bit bolder because after many decades of working on this, I can see the end of the tunnel, and it's bright. Thank you very much.
Adam, thank you. Spent a fair amount of time on the convection. Do you actually have significant shear stresses developing during the convectives? Are you actually modeling that properly?
Properly. It's a resolution issue. Shear is viscosity. And viscosity is numerical, unfortunately, and it doesn't really follow the viscous, but there's real viscosity. The viscosity is due to neutrinos. And to handle it properly, you have to have the velocity-dependent terms in the transport, and you have to have the momentum coupling to get the shear viscosity. The bulk viscosity comes from the out-of-whackness of the neutrinos. They're not necessarily in a Fermi distribution with a chemical potential and a temperature. If they were, then that's beta equilibrium. That's what neutron stars are like without neutrinos. And that wouldn't generate any entropy. But if they're a little bit out of whack, which they can be in a dynamical context, when you do all this, then you have bulk viscosity. And those are handled. It's just the bulk viscosity is probably visible. We can see the effects. And the numerics doesn't suppress that. The shear viscosity, I'm not convinced that we have that right. But the physics is in there to do the viscosity, to handle the shear, if that's what your question was.
Thank you.
Sure.
Yeah, just to kind of follow up, so are like the resolution, the changes with the resolution were impressive, right? We got exploding stars versus none. Are those results already converged?
No. We're at least seeing that as we go up in resolution beyond that everything is, everything that should, once it started exploding, they're all still exploding, and they get more explodable. If you looked at the difference between the medium default resolution and the high resolution, it wasn't that much different in the development of the radius of the shock and these sorts of things. So there are a lot of similarities. The neutrino luminosities are almost exactly the same. So the neutrino physics has converged. Given the microphysics we put in, that's converged. But the hydrodynamics, I'm not going to claim. And we can see that in the Kolmogorov light spectrum when we do when we find the spectrum of the turbulent kinetic energy, for example, as a function of wave number, or approximate wave number. We're actually doing it in the YLM-Ls, but it's like wave number. We have converged at low Ls, but not at high Ls. And as we get more and more of those Ls in there, the turbulent stresses get a little bit larger. But there's not a lot of stress missing, and the low Ls are converged.
Does your model work in gamma ray bursts too?
No. This has to be purely it has to be general relativistic to do that, and that's an interesting point. We don't have rotation in here. We did 10 years ago. We did a calculation with a different code in axisymmetry, but with magnetic fields. And what we saw was that with rapid rotation, the free energy of the differential motion of the object that was formed was a great source for generating magnetic fields, which were also coupled to the outer material, and you get this tunnel boring machine. You got the bipolar jets, and those jets could give you 10 to the 52 ergs. That's only with really rapid rotation. With really rapid rotation, it's really hard to suppress magnetic fields. But if you form a black hole, which people think that is associated with a long soft gamma ray burst, perhaps in the collapsed star context, you always go through a proto-neutron star intermediary. You can't go to a black hole directly if you start out with a Chandrasekhar mass. I can go through the details of that. It's a very simple argument. So you always form a proto-neutron star. So it could be rapidly rotating, though, because the GRB is supposed to be a rapidly rotating black hole that gives you a jet, a relativistic jet. You're always going to have a precursor non-relativistic jet if you eventually have a relativistic jet. That precursor jet in our simulations could give you 10 to 52 erg explosions. If it's really rapidly rotating, this is a few millisecond periods, but not 2 millisecond periods. That's really fast. So that's not going to be the common case. But if you do want to form a GRB, you go through this proto-neutron star intermediary, you're going to get this very strong jet coming off. It's going to be non-relativistic because it's baryon loaded. If you have a neutron star there, you'll always have a wind going along the poles. That's going to baryon load the axis. If you baryon load it, you can't get up to high gammas. You need high gammas for the gamma ray burst. Then you form the black hole. Black hole has no surface. There's no wind coming off it. It doesn't fill the the axis. You can have neutrino and neutrino annihilation producing pairs along there. Those are relativistic particles. So you can get a relativistic jet only after you form the black hole. It has to be rapidly rotating. If you have the rapid rotation that led to a black hole, you'll have a rapid rotating proto-neutron star. That will have a big explosion, and that will be a precursor. This is a precursor only 5 seconds earlier, that type of thing. 10 seconds is about the light travel time across some stars. Okay, so it's an important timing thing as well. But you could have most of the energy in the non-relativistic jet that's MHD driven, and then the gamma ray burst the jet that's associated with the gamma ray burst that you see along 5 degrees comes right afterwards. And it will be sub-energetic. It will be sub-dominant energetically, but dominant relativistically. We have not simulated this. We've simulated the first part, but not the second.
What you mentioned, Adam, early on in your talk that you have not been able to really do the black hole problem, formation problem. What do you think of Stan's group's Supercold and company's bifurcation plots showing neutron star versus black hole formation as a function of progenitor mass? And it's all ascribed to either compactness or neutrino.
Compactness does not map to explodability. We published this. Everybody who's doing the models, even people on that paper, don't see that. There's another prescription, the early prescription, which is multiple parameters, a little bit closer. But you saw how sensitive some of those models were. We don't know. Compactness is not the parameter. We know that that's not the case because we need the high compactness ones to give you 10 to 51 ergs. The low compactness ones can't give you 10 to 51 ergs most of the time. But everybody thinks that low compactness is essential. You don't have any mass there upon which the neutrinos can be absorbed. Your luminosity is lower because your accretion rates are lower. And the energy deposition goes as luminosity times that mass, optical depth. And so it doesn't really work out very well. In the past, to do nucleosynthesis, people had really, really crude models of explosions because they couldn't wait for theorists to give them what exploded. So they had a kinetic energy bomb or a thermal bomb. These things were really, really crude, but the nucleosynthesis was state of the art. But it turns out, of course, that how you explode really makes a difference, particularly for iron, silicon, sulfur, argon, calcium, intermediate mass elements that are close. Carbon, oxygen, that's progenitor stuff, mostly. Nitrogen is progenitors. And so people were looking for a better way of doing the explosion so they could do the nucleosynthesis. So people have now found other approaches, more or less 1D approaches that are parameterized to explode. Calibrated on the crab may have had 10 to 50 erg explosion, and 87A had maybe 1.5 times 10 to 51. And that's really not the right theory, but it's better than what people did in the past. And the result is that people can make some sort of predictions for what explodes and then what the nucleosynthesis is and what gives you a black hole and not a black hole. It's an approach that we really can't do much better on because we can't do all those simulations and each simulation has its caveats. So we're not there yet. I would say that it's likely that the lowest mass progenitors from 9 up to 20 solar masses are going to give you neutron stars, and there's going to be a spectrum of energies from 10 to 50 to 10 to 51 ergs in that range. Most of those are going to be neutron stars. It may be all of them. As I said before, you're going to form black holes when the binding energy is tough and the explosion is tough. And that's probably with really high compactness. But modest compactness that would be eliminated as an explodable model by these particular approaches has to explode. And that's what everybody's seeing, in fact. So I think it's an approach, but it shouldn't be taken too seriously. And it's done to further other goals, to try to give people some sort of sense. But what has emerged, and I think that's true, is that there's not a simple mass above which you form black holes and below which you form neutron stars. I think that's going to survive. I just don't know what the mapping is, and I will say nobody else does either. I could say more. The last question here.
I was curious about the neutrinos. Given the asymmetry of the explosion and so forth, what is the most important thing you think you're going to learn from the detection of neutrinos on the Earth?
It's hard to say. From 87A, as I say, we had 19 events and there were 300 papers in the first 2 years. Now, how much did they learn from that? We're going to get thousands of events if we're lucky. The detectors have to be on, has to be in the galaxy, but thousands of events. And then you'll be able to have a light curve. And the variation of the light curve tells you, for example, if you have a really good light curve, you can see the time variability of the convection. So you can actually get the time scale of convection. You can back out the position of the shock before explosion, so you can get the radius of the shock. You can get the cooling of the protoneutron star in the first seconds. Okay, so you can see how it's actually shrinking. If you have the gravitational wave stuff, you can even do more. The neutrinos are the big. You can see the explosion because the luminosity changes. Because you're mostly, it's, as I said, you have simultaneous accretion and explosion, but you still decrease the luminosity a bit. It would decrease much more if you didn't have the simultaneity. The problem is that the neutrinos are going to be emitted in differently in different directions.
Exactly.
We see, as I said, about a 5% variation with solid angle. That's not large, but you have to think about that. But it's the time variability of that it really tell you something about it, because you're just looking at the time variability of the stochasticity. As I mentioned, you have AM modulation with some of that, because the accretion is modulated with certain models, etc. So I actually think, getting back to that 300 paper thing, when we have a lot of events, we're going to learn a lot more, not proportionally. I mean, like gamma ray bursts. There are 150 models and 20 gamma rays. It changed, right? There are fewer theories and a lot more data, and that's the healthy direction. And I suspect that we'll learn a lot, but there won't be as many papers.
All right, let's give the speaker another round of applause. Devoid of neutrinos, it has a few electrons left, and you'll have a neutron star. So that will be active.